So when doing graphs of sine and cosine and tangent, it also helps to, well, first of all, you have to know how the basics work. So you have to know, for example, what they look like by starting out. In other words, you have to know what sine looks like on its own or what cos looks like. But it helps then to understand about transformations. And hopefully you've learned about these before, but for any function y equals f of x, we have some rules about transformations, and I have just a few examples here just to sort of help illustrate this. So if we have any function, this could be anything at all. I'm just using this to sort of jog your memory here. Let's just say we have some function f of x, and let's say that's a quadratic. Let's say it's like x squared. So that means if I drew it, I would have some sort of, x squared would sort of look like this. This is what x squared would look like. Some sort of dotted line like this. I would use this as a reference. What f of x plus 2 does, adding a number after the function, so in this case, this would be like the graph of y equals x squared plus 2. This would be the example. Then it would look just like this, except this whole thing would go up by 2. So in other words, it would be like this. So the key thing here is this one right here would mean up by 2. And over here, for example, this would be down by 1. So a graph like that would it would be just like this graph, except it would be down by 1. So this is the first kind of transformation, is adding something or subtracting something after the equation. Then that just brings it down by 1. And if you want to see, or up by 2 or whatever, if you want to see an example of that second one, of this one here, f of x minus 1, I can draw that one. This is the dotted line, what it would normally look like. And then in fact, what it would do, it would look just like it, except it would be down by 1. So it would go like this. This would be y equals x squared minus 1, for example. See, we don't need a graphing calculator to do these. If you understand transformations, start off with some original function and then shift it or move it or stretch it or whatever you need to do. So this is the first one. We call this right here a vertical transformation, or vertical, yeah, we could say translation, because you translate it up or down. So this means you drag it up or down. We have another kind. This right here is called a horizontal translation. So I'm going to write that down. So horizontal translation. So something like this, for example. Now, I want to show you this because these ones work opposite to what you expect. Okay, so I'm just going to show you this. So here again is my sort of starting out x squared. Let's just say I keep using that as an example. If it's within the parentheses here, you would think, oh, minus 1, that must mean it goes left by 1. But it turns out this goes right by 1. In other words, it does the opposite of what you expect. This is really important. Okay, so opposite of what you expect. This is important. So in other words, you think it goes left by 1, that means it goes right by 1. Therefore, this graph would be something like, maybe like this. So it's just been shifted to the right. That'd be the equation of y equals, and in brackets, x minus 1 squared. So if I keep using x squared, then this would be my function. Now we have, so instead of just dragging it up and down and left and right, we can also stretch it. So this right here is going to be called a vertical stretch. And this one here, for example, this will stretch by, we say, a factor of 2. So for example, if I looked at this one would be a little bit harder to tell, but let's say I started off with some other function. Turns out this here would stretch it up and down. It would make it stretch more. In other words, if this here is how it looked, it would actually take it and it would stretch everything, let's say, up a little bit. So everything here would sort of, if it was over here, it would be twice as high, and over here it would be twice as high. So it would stretch it up. So here would say a stretch by a factor of 2. And the equation of that one could be like y equals 2x squared. And then we have something called a horizontal stretch, and I'm sure you can figure that one out. Here we go, we got horizontal. Now, if we do this one, though, it works a little bit differently. Remember I said if it's within the brackets, it does the opposite of what you expect? Well, same thing in here. In other words, here I would expect, oh, a 3x means it must stretch it horizontally by a factor of 3. Nope. That means it's going to, well, you could say it will compress it. Compress by a factor of 3, let's say. Or you could say it stretches by a factor. You could also say this. You could say it stretches by a factor of, you could say 1 over 3. In other words, it gets sort of 1/3 as wide. So this also could be, you could do that. So this here would be something that would squish in the x direction. Now using x squared isn't a very good example because it'll kind of look the same, but we could do that with like any graph. In fact, we could do it with some sort of curvy graph. Let's just pretend it was something like this. We're going to get to this in a second, actually. Something like that. If I did this stretch, let's say 3x, then this here would actually be, you know, sort of compressed by 3. So it would be something that would be a lot thinner, a lot sort of more squished. So this whole thing right here would be all squished. So I'm not sure exactly how it would go, but it's something like this right here. Of course, it'll be even more squished than that, but I just want to give you a rough idea what it would look like here. So this here would be squished that way. And of course, if it was on this side, it'd be squished that way as well. So it'd be squished towards the y-axis. You'd have to figure out exactly how much, and in fact, I didn't draw it quite right. It should be even more, but so be it. I'm just trying to show you. It should be a lot smaller. It should be less than half, in fact. So I've actually not done it very well here. This one here should be much shorter. But just this is the idea behind it. Now what I want to do then is take these and try to show you what to do with them. I mean, we also had other things you could do, like a negative in front of it, flips it over the x-axis, and if you put a negative inside, it flips it over the y-axis. But let's just do some of the concrete examples, but this time with sine and cosine. So this is the general equation for a function that's sine. So in other words, we write it like this in general. We say f of x equals a sine of b in brackets x minus c close brackets plus d. And we're going to just slowly take our time and go through each of the equations with, you know, focusing on each of the different letters. So you see, we're going to actually slowly go through sort of what's a, what's b, what is c, what does d tell you. And we're going to do a few examples just to show them. So first of all, a, what does this tell you? Well, remember, just like our functions before, a number in front of it, that tells you that's a vertical stretch. So just like over here where it was like y equals 2f of x, that was a stretch. So in this case right here, this is what we call a vertical stretch. This is important. Vertical stretch. Now, what this really tells you is this. We actually have this equation here. We have that the absolute value of a is called the amplitude. This is going to be really important. So when we do these graphs, if we take the absolute value, it's just because this might be negative. Then if we take the absolute value of a, we get the amplitude of the graph. That really helps us to draw it. So let's do an example. Let's do y equals 2 sine x. And I'm just going to sketch this one. So if I do this, I need myself axes like this. So I'll go like this. And when I draw this, then I can just really cheaply actually just draw myself something that just goes up and then down and then back. That's what a sine x looks like. Now what does the 2 mean? It just means that it'll be twice as tall as it normally would be. So here's the good news. See, I just draw it like this. I say, oh, the period is still the same, so I know then that this right here is going to be 2 pi. I know this right here is going to be pi, because that's half of that. Then I go half of that, that's pi over 2. And then I start working my way backwards. If this is 1 pi over 2, 2 pi over 2, so that must be 3 pi over 2. Keep in mind, it keeps going forever, right? I just want to show you just one period of it. It keeps going back here too. But the important thing is that the value up here, it doesn't go from 1 to -1 like it normally does, because we've got 2 here. We've stretched it by a factor of 2. So because of that, this right here is 2 and this is -2. So that's the key thing right here. That's the way to deal with that one in particular, is just because it goes up by 2 and then down to -2. That's it. That's how you deal with that one. So let's do another example, just to make sure this is clear. Let's do y equals 1/4 cos x. Well, it helps right away before starting off to actually draw what cos looks like. Remember, cos starts off at 1, so it goes, I'll just draw one period of it like this. Of course, it keeps going. Now, what is its amplitude, though? What is its value right here? What is this value, and what's this value? These are the key things. It goes up to 0.25, because that's 1/4, and it goes down to -0.25. Isn't that easy? There's nothing to it. And of course we have to label these values. This is still 2 pi, we haven't changed that, and that means half of that is still pi, and half of that is still pi over 2. And we go 1, 2, 3 pi over 2. There, we've fully drawn this. This is actually the sort of 5 points you needed to draw this. Of course you just keep it going. You could extend it as far as you want, back and forth. But that's how you can draw this. So you can see, hopefully, that once you learn some tricks about these transformations, these are completely doable. Okay, you just got to be really, really careful with what each of the letters means. Take your time and write down what it does for you. So in this case here, that just tells us about the amplitude here. So maybe I'll write that down here. Here, the amplitude, I'll just say amp, like that, equals 2. Over here, the amplitude equaled 1/4. In other words, 0.25. But we haven't messed around with the period, so the period is still 2 pi. Over here, the period is still 2 pi. So that's the key to these. Now let's do another kind. Let's work on b. b tells you, if you remember your transformations here, that's like putting a number inside the bracket. So that would be like this right here. This right here is a horizontal stretch. So this right here, that's what this is. This is a horizontal stretch or compression, of course. Now what's really important is this. People think that b tells you the period. Well, it does. It gets you the period, but this is the most important thing here. b is not equal to the period. It's not equal to it. b is related to the period, but it's not equal to the period. Okay, so actually we can say that the period of the graph is actually 2 pi over b. Or if you're doing it in degrees, because this is 2 pi, that's radians, we could also say it's 360 degrees over b. So you could also say that if you wanted. But this is the main thing that we use here. This is the main one right here. So we sort of use this one right here. Just like over here, this first one right here, we could say that A is the amplitude. That's the important part here. And over here, we just said that B is not the period, but it's almost. I mean, B gets you the period. Now it works opposite to what you might think. Remember, because it's in the brackets. So if you think, oh, a 2x, that must make it go twice as, you know, it must stretch it by 2, then it actually shrinks it by 2. It makes it twice as small. Now, if you're not sure about these, it really helps to just figure these out here. So let's look at this. Let's look at what's the amplitude here. The amplitude is just a number in front here, so that's 1. But the period, let's figure that out. The period is not equal to 2, because this is, we have that b is 2 here. So the period is not 2. The period is 2 pi over 2. And in that case, 2 pi over 2, that gives you pi. Therefore, the period is going to be pi. So I just got to draw myself a sine curve that has a period of pi. I can easily do that. And again, if you do it this way, I think it's really easy. Just take this, make yourself one period of sine curve. You know, it goes up to 1 and minus 1 because that's the amplitude. But then you just start labeling it here. You say, oh, well, I know what this is going to be. I think I want to do this in blue, actually. Like this. So the difference is you have to label your period. This value is no longer 2 pi. Now it's just pi. If that's just pi, what's this? That's half of it, so it's pi over 2. And then we take this point over here, this peak, that's at half of pi over 2, so that's pi over 4. Then we start counting by pi over 4. So 1 pi over 4, 2 pi over 4, so this must be 3 pi over 4. That's how we deal with these really weird ones. And of course it keeps going forever. You could extend it as much as you want. And let's do another one maybe. Let's do cos of 0.5x. So again, this might sound really complicated, but it helps to just write down what you know. I know that the amplitude, the number in front of cos, that's just going to be 1. And the period in this case is going to be 0, well, it's going to be 2 pi over 0.5. Now what does that mean? 2 divided by 0.5. This is like saying 2 pi over, 0.5 is like 1/2. If you remember what you do with when you divide by a fraction, you multiply by the reciprocal. Now you multiply by, instead of this 1 over 2, it becomes 2 over 1. So that gives you, let's see, that's just 4 pi. So because of that, I know my period is 4 pi. So I just need to draw myself a cos. So one period of cosine. So I'm just going to go, let's say, from here to here like this. And of course I can keep going. But what I would do then is on this one right here, I would just label it conveniently. So I would say, oh, okay, well, whoops, I meant to do it in blue again. So I'll just go like this. So I would, of course, just label then, well, the top right here, this is 1. This is at minus 1. And the important thing is that here, this end, this is 4 pi. If that's 4 pi, then half of that is 2 pi. If that's 2 pi, half of that is just 1 pi. Then we go 1 pi, 2 pi, so this must be 3 pi. Do you see how I do these? I hope you see it's not actually quite so crazy as it might seem.